Let's take a look at the effects of squat. When a ship proceeds relatively through the water, she pushes water ahead of her. In order not to leave a hole in the surrounding water astern of the vessel, this volume of water must return down the sides and under the bottom of the ship. The water streamlines that flow astern, and this flow is speeded up under the ship. The increased velocity of the water, by following the law of conservation of energy as described by Bernoulli's principle for fluid dynamics, causes a drop in pressure, resulting in the ship practically dropping vertically in the water. As well as dropping vertically, the ship generally trims by the head or by the stern. The overall decrease in the static UKC, under keel clearance, forward or aft, is called ship squat. It is important to note that squat is not an actual increase in the draft, as in reality the vessel's displacement remains the same, and therefore the true mean draft should remain the same. However, due to the trough created at the middle section of the vessel, which happens to be the section offering the most buoyancy, the vessel moves further down in relation to the sea bottom. This causes a reduction in the under keel clearance, which if not allowed for may spell disaster, resulting in a ship grounding. The risk of going aground due to squat must obviously be considered when operating in shallow and restricted waterways. The navigator must calculate to allow for squat during voyage planning to ensure that the vessel will still have a sufficient UKC for safe passage after allowing for squat. The two main factors affecting squat are speed and the block coefficient. For open water, the formula below is used to calculate squat. Squat equals the block coefficient times velocity squared divided by 100. For confined waters, the below formula is used. Squat equals the block coefficient times velocity squared divided by 50. We know what the speed is, so let us discuss the block coefficient. The block coefficient is considered as the ratio of the underwater volume of a ship to the volume of a rectangular block, the dimensions of which are the length between perpendiculars, the mean draft, and the extreme breadth. The relationship is expressed as a decimal figure. The block coefficient can be calculated by the following formula. Block coefficient equals the underwater volume divided by the block volume. The block volume equals the length multiplied by the breadth multiplied by the draft. Another important factor to keep in mind is the trim that may be experienced due to squat. As already explained at the beginning of this lesson, when a vessel is moving through the water, it is essentially creating voids in the water, which in turn the water tries to fill by moving along the hull and under the bottom. We can also understand that vessels having a finer form, such as passenger vessels, tend to obstruct the water flow less at the bow when compared to their mid and aft section. On the other hand, full-form ships, such as bulk carriers and tankers, which have a much fuller bow, tend to obstruct the water flow more at the bow. This difference causes the low pressure to be located at varying positions for both types of vessels. While for passenger ships and the like, the low pressure will be aft of midship, thus causing a trimming moment by the stern. Bulk carriers, tankers, and other full-form vessels having a fuller bow tend to trim by the head, since the bow obstructs a considerable amount of the water flow, and thus the low pressure will be located forward of midships. During all stages of voyage planning, the navigating officer shall ensure that sufficient under keel clearance is maintained. Being aware of under keel clearance levels commences in the appraisal and planning stage and continues throughout the execution and monitoring stages. When calculating the UKC, the navigator shall take into account the effects of squat, heel due to wind, heel when turning, list, trim, movements of the vessel in a seaway, any appendages to the hull, changes to the sea bottom such as sandbanks, and hydrographic survey accuracy. With all the above variables at play, it may be difficult to accurately calculate the vessel's under keel clearance. This shows the importance of allowing a sufficient UKC to permit for all these variables while still maintaining the ship in a safe condition. The actual under keel clearance can be reconfirmed when the vessel is proceeding in the area and starts to experience squat against what was calculated for that position. This will allow the OOW, officer on watch, or the master to reassess if the vessel is proceeding at a safe speed in terms of squat, or if it may be safer to reduce the speed or perhaps be able to increase it. By knowing the actual UKC and the expected UKC in the same position, we can reconfirm the actual squat with the calculation and ensure that the UKC policy of the company is adhered to. In case we discover that the squat is more than expected, then we can recalculate at what speed we should proceed to be able to comply. It is therefore beneficial for the seafarer to know when the vessel is experiencing squat. There are various signs which can indicate that the vessel is experiencing squat. Having knowledge of the below squat effects can help navigators be more vigilant and keep an eye on the echo sounder. These impacts include the ship generally developing extra trim by the bow or the stern. Wave making increases, especially at the forward end of the ship. The ship's steering becomes sluggish. Draft indicators on the bridge or echo sounders will reveal changes in the end drafts. Frictional resistance is increased by squat as water flow velocities are increased along the midships region of the hull. Engine RPM will decrease to compensate for the load on the engine. The ship may start to vibrate. Mud showing up around the ship's hull. The vessel's rolling, pitching, and heaving is reduced due to the dampening effects produced by the narrow layer of water under the hull. Turning diameter of the vessel increases. It can become as much as twice to that in open sea. The diverging wave pattern will appear to widen, and any initial list or heel that the vessel may have tends to increase. As it is clearly seen from the formula, and as already explained earlier, the only two variables that are in the control of the ship's crew to determine the extent of the squat experienced by the vessel are speed, the initial under keel clearance UKC, and available surrounding water. Speed is the most influential factor governing squat, so slowing the vessel down will have the most immediate effect in reducing squat and improving control over the ship, provided that steerageway is maintained. The other variable, available water depth, is not so easily controlled once the vessel has committed to the route.